Welcome everyone. My name is Ken Gorton. I am a solution engineer on the national government's team in Washington, D.C. with Esri. With me this morning is R.J. Sunderman, a product engineer on the real-time and big data team. And this morning we'd like to walk with you through a little bit about GeoEvent Server and how to perform real-time analytics using that platform. We'll start off with some fundamentals about the platform and how it enables real-time analytics, some of its capabilities, and the main components of GeoEvent Server that you'll work with in setting up real-time services. Then we'll present a few use cases that will hopefully illustrate how these different analytical tools can be put together to form various workflows and process event data, examine it for crucial conditions, and then forward actionable information to output streams that so you can make informed decisions. And then finally, we'll walk through some of the other opportunities that you'll have both within this conference as well as outside afterward, where you can dig deeper into GeoEvents. So I'd like to start out with a little bit of a high-level overview of some big picture concepts about GeoEvents, about our real-time capabilities really, as well as our big data capabilities in ArcGIS Server. Now there are a number of key roles that this capability plays with ArcGIS Server. And first is simply bringing data into the system in real time. This is one of the main capabilities of GeoEvent Server. It allows you to receive that information without human interaction. So sensors will send their information in real time just as quickly as that information is being produced, and your system then can receive that in real time. Second in the list here, of course, is being able to process that information. That's what the bulk of this workshop is about this morning. And the real-time capabilities allow you to process that information and look for certain conditions and certain gold nuggets in this sea of noise of information that very often inundates us in our systems. And then generating new streams of data. When certain information comes in that we have configured our system to consider to be important, maybe we want to send that information on in the form of alerts or simply log the information in. So output streams are another capability of our real-time and big data processing. Visualization of large quantities of data has for a long time, it's a challenge. It can be a real challenge. Inundating a map with features renders it useless. So we've also developed certain capabilities to be able to visualize enormous quantities of data on a map without sacrificing performance or visual quality of the map. In addition, because we need to be able to store huge amounts of data, big data, we've developed the Spatial Temporal Big Data Store to enable that kind of not only rapid ingestion of data, as GeoEvents will produce huge streams of data. We were having challenges being able to write those the data into, say, a feature service. And so the Spatial Temporal Big Data Store fills that gap, allows us to pump huge quantities of data in very rapid order. And then the Big Data Store also supports batch analytics, the geoanalytics, and being able to process that data on regular basis. So now, real-time services are defined within a service designer. And so this is what we'll talk about with it in this workshop this morning. But GeoEvent services are really what define the flow of messages within GeoEvent Server. They are configured using a service designer, something like you see on the screen here. And it's similar to Model Builder in ArcGIS Desktop if you've used that before. The difference here is that you're working with GeoEvent elements rather than geoprocessing elements. GeoEvent elements will be things like input connectors and output connectors, as well as the processors and filters that analyze the data as it's moving through GeoEvents. Now, the role of any input connector, represented by the green rectangles here, is to receive incoming data, translate them into discrete messages, what we refer to as GeoEvents, and send them then on into GeoEvent Server, where they can be acted upon and examined by the different processors and filters. Similarly, the outputs take a GeoEvent message and translate it into some sort of output format appropriate for its destination. It could be a tweet, or it could be an ArcGIS feature that's being written into a feature layer. Now, as GeoEvents propagate from inputs to outputs, it's the processors and the filters that act upon them. Those are represented by the yellow rectangles and the yellow diamonds, respectively. And they perform certain actions on the GeoEvents as they move through as they move through the system. They might be modifying some of the attribute values of a GeoEvent. They might be modifying the geometry of a GeoEvent. And all of these things work together, they might be looking at certain conditions within a GeoEvent and then generating new messages. Filters, as the name implies, they act to stop the flow of processing. If a GeoEvent doesn't meet a certain condition, that filter might simply stop it from going any further. So a bit about connectors. The input and the output connectors really provide the conduits through which GeoEvents enter and exit the system. We have configured a number of very commonly used connectors that you can use, or you can configure some of your own based on the available components within GeoEvents. Some of the common ones would be to watch a TCP port, or listen on a WebSocket or a REST endpoint for client applications to send in XML or JSON or comma separated values, whatever the case might be, or to actually actively poll on regular intervals, say a feature service or a web page for data. Now, there are also a lot of very specialized connectors that that are really tailored for very specialized inputs. Things like receiving tweets or Instagram or common alerting protocol messages, and these are also available to you as well. Now, many third parties have also written a number of connectors and shared them, and you'd probably be able to find many of these on the gallery and in ArcGIS Online. So before you start thinking about either building your own or going to extensive lengths to find a new input connector, you might just look for one that could be configured for your use. And in most cases, that can be done. Now, similar to input connectors, output connectors take those GeoEvents and they translate them into outgoing messages. We have a number of output connectors that you can configure, again, to do many of the most common types of outputs: text, XML, JSON, ArcGIS features, and so forth. A number of specialized output connectors also will do things like send a tweet, or right into more specialized output destinations. And as always, if none of the connectors will meet your needs, there's a Java SDK that you can use to write your input or output connectors as well. Now, processors, in between the inputs and the outputs within a GeoEvent service are the processors and the filters. And we'll highlight a number of these processors this morning. Many of these out-of-the-box processors are available to you to be able to manipulate GeoEvents as well as watch for certain conditions. And we'll look at a variety of these processors as well. And just as with the connectors, you can write your own if none of the existing processors meet your needs. So let me show you this a little bit of an illustration about how we can interpret real-world events and analyze them in GeoEvents. In this construction zone, you see a number of vehicles moving around. There we are. And we get a number of different kinds of visual feedback. One is the vehicle's icon is moving around the map. As it moves across the ground, we're getting its location updates. Now we're also seeing a breadcrumb trail behind it, so we have a history of where it's been. In addition, as vehicles move from one zone in the construction zone to another, we have notifications of that fact. And then over here on the right side, where one vehicle's actually left the construction zone for a while, that's a more serious thing, and we have a different kind of alert that lets us know about that. So let's take a look at what the service might look like that enables that sort of information flow. If we just take a look at this one service, we know there's a single input that is receiving the location messages and the status messages from each vehicle over here on the left-hand side. And the first part of this workflow simply sends those messages onto an output. And this is what updates the map with the current location of a vehicle. Other portions of this service tag the vehicle message, tag that GeoEvent with the portion of the construction zone, the individual sub-area that the vehicle is currently located in, and then sends that message on. And then it provides our breadcrumb trail of history, so we can always go back and look at where a vehicle was at a certain time and what zone it was in. Other parts of the service designer alert us, give us notifications when a vehicle moves from one zone to another. These are routine alerts. Something that wasn't illustrated in the video was the ability to, any sort of a notification of attribute status of a vehicle. Suppose that it reports that it's low on fuel as part of its regular status update message. We could watch for that kind of information and then send an alert to make sure a fuel truck gets out there to service that vehicle. And then finally, we have a notification where if a vehicle actually leaves the entire construction zone, that's something a little bit more serious that we want to address. And so each one of these workflows, each one of these information flows is supported by this service where we have one single input and a number of different analytical steps and then multiple outputs. So of all the processors that we're using, we use a number of processors as well as a filter there. And the processors, I want to make a point about the processors. You notice that some of them worked on the geometry of the GeoEvents. Others worked on attributes. Some things that work on geometry, things like buffering or intersecting, finding out if one of those vehicles was inside a particular construction zone or all the construction zone areas. Other things were acting on attributes. The filter took a look at the fuel status that was represented in one of the messages. Now, some GeoEvents, such as those the elements that alerted us when the vehicle moved from one area to another or left the construction zone, simply watch for certain conditions. These could be spatial conditions or attribute conditions or a combination of both, and generated entirely new messages. So rather than just moving the incoming message along, they watched for a condition in that message, and when the certain conditions were right, they sent an entirely different kind of GeoEvent. So processors do a lot of different kinds of actions on GeoEvents. But the role of processors, generally speaking, is to propagate the flow of information. They want to either modify the GeoEvent and send it along, or generate a new GeoEvent and send it along. In either case, they want to keep that message flowing. Filters, on the other hand, really have the exact opposite role. They want to stop the flow of messages unless the message meets certain conditions. And if the conditions aren't met by a filter, then that message won't go any further. So in the case of any sort of condition, whether it's in a processor or a filter, we can combine spatial and attribute conditions, and we can string multiple conditions using Boolean operators and or negate them with a not. Now, a word about spatial operators within GeoEvents. The original, the initial version of GeoEvents had 3 spatial operators that were really suited to comparing the geometries of point GeoEvents with polygon geometries or geofences. At 10.3, we significantly expanded the list of spatial operators that we they included with GeoEvents and now supports GeoEvents that could be points or lines or polygons, and all of those are supported by GeoEvents. And as well as with other geometries, in finding spatial relationships in much more robust manner. So we now have something like 11, 12 spatial operators within GeoEvents.
I wanted to take just a moment and discuss some of a common confusion when working with geofences and the filter expressions that you use in both filters and processors. There is a scope, any versus all, with the spatial operators that Ken was just highlighting that sometimes generates confusion with the selection of geofences for the operation. Here on the screen we see a couple of example expressions. Geometry intersects all is going to look for the events geometry to simultaneously intersect all of the geofences. The dot star is also selecting all known geofences, but the two alls are not the same. The dot star is selecting geofences from any category, the second dot star with any name. The second expression, geometry disjoint any, is looking for the events geometry to be disjoint from any single geofence in that selection set. And again, with the dot star, we're selecting all of the geofences, so that is our selection set. If we look at this as an illustration, we have a vehicle track line depicted here in which the vehicle is reporting periodic positions. The intersect any is evaluating against these 3 chosen geofences, and it is alerting us, visually or otherwise, when a truck vehicle's position intersects geofence A, intersects B, and then later intersects geofence C. But if we wanted to intersect all of the geofences, of course the geofences would have to overlap. So now you're not dealing with a US counties or a United States type set of geofences, you're dealing with something that the geometries could legitimately overlap. Geofences inside GeoEvent Server are organized in memory in an efficient structure for the real-time processing and the analytics that we go against. We are not looking at feature services to get the geometries. Those need to be imported into GeoEvent Server. So one way to import them is to simply do a one-time import from a feature service. That takes a snapshot and is good for static geofences, like I mentioned, counties, operational areas that don't particularly change, US state boundaries. You can also periodically synchronize with a feature service so that as the features change, you bring those new geofences in to apply to your analytics. One of the challenges here is how often do you want to do that synchronization? If you were to be polling the feature service only once every 60 minutes, and it was just your bad luck that on the 61st minute a very key change was made to one of the geometries in the feature service, all of your real-time analytics would be working for the next 59 minutes against that old data. To address this challenge, when geometries are going to be expected to change and possibly change very rapidly, you can synchronize your geofences in GeoEvent Server using a stream service. A stream service is a capability of broadcasting the event records that you're processing over a WebSocket so that any client can subscribe and retrieve the information. GeoEvent can subscribe to its own stream service in order to synchronize geofences. Taking a look at this as an animation, let's say that we have a point come in that has a location, and what we're really interested in is when another feed's geometries intersect or have some spatial relationship with the area around this particular point. So we use GeoEvent Server to create a buffer, and we push that buffer out of stream service. Because what we're interested in detecting is when the points from this aircraft intersect that area for the first event. So when that point location changes, the buffer, of course, is redrawn with the new event, pushed out the stream service, and now that commercial aircraft path we can see has an interaction or a spatial relationship with the changing geofence. You can think of this, for example, maybe an exclusion zone around a ship as it's leaving port. You shouldn't get too close to an aircraft carrier because they're very big and they don't stop very fast. I'd like to take a look now at a different type of analytic that is identifying conditions. In this model, we're going to have some electric transmission lines going through the Los Angeles area in Southern California, and there's going to be a storm that comes on site and begins intersecting some of those polyline geometries. In my GeoEvent Manager here, I have turned on a GeoEvent service that is going to be processing the storm polygons. I've also turned on a simulated input that's receiving some event storm polygons from my simulator over here to the left. And then a couple of outputs, one to send buffers of the transmission lines, one to display intersections, and one to display the storm polygons. If I take a look at that on a portal web map and simulate an event, here's our storm as it begins to come on scene. And as the storm advances, it will intersect some of the polylines. The true intersection is highlighted there in orange, whereas the overall intersection is using a buffer to highlight the entire transmission line. Let's take a look at what the analytic looks like behind that particular demonstration. The first part is simply pushing the storm's polygon out of stream service so that you see the storm represented on the screen. Up on the top, I have a geometry intersector that is responsible for clipping out or looking at just the intersection, that portion that was highlighted in orange. The body of the analytic is using several different processors. It's using a geotagger to identify which polylines it intersects. It is splitting that event record so that every event record has only the name of one intersecting polyline. It's then using a field enricher to replace the storm's polygon with the polyline that the storm is intersecting and then buffer that polyline. That's how I'm pushing out that highlighted area that you saw on the map. If we take a look at Field Mapper as just one of the processors, the Field Mapper is responsible for adjusting the schema of an event definition. You often are going to be working with JSON, GeoJSON, XML, things that have very rich, complicated hierarchical structures, possibly even lists. Those sort of structures can't be represented in Esri feature JSON before you want to put items into a feature service, for example, or pass them out to a stream service. So you use the event field mapper to reorganize that schema. For example, let's say I receive in a sensors report and it has a unique track ID, but it has a bunch of other information that I'm not particularly interested in passing along to my subscribing clients. I want to simplify that event record, so I'm only giving the track ID, the reported date, the geometry, and maybe a category. I use a field mapper to map track ID to track ID, date to date, geometry, and category across, and thereby simplify the event. I could also be using the field mapper to select given items that are children or sub-elements of a JSON structure in order to flatten out and simplify the output record. Another one of the processors I mentioned was the field enricher. Field enrichers, as the name implies, enrich an event record. They use an attribute join to retrieve additional information from a secondary table. For example, I have an event record here for a sensor, and that sensor has a track ID. I also have an external table, either as a file on disk or as a feature service, that lists out a whole bunch of the different track IDs for the expected sensors that we're going to be working with. By performing an attribute join with a field enricher on the track ID, I can pull additional information, such as another sensor that this particular one shouldn't come in contact with, or a simple English description of some condition. So the field enricher then enriches the output record by appending that no contact and no entry information. The field enricher can also be configured to write to existing fields. The buffer creator is one of our geometry processors. It constructs a polygon around an event's point, polyline, or polygon geometry and can either enrich the event record by adding that new polygon to the event record, or it can replace the event record's geometry. For example, here I have a point coming in, and I can buffer point, polyline, or polygon and add that polygon to the event record, or replace the inbound event's geometry with the new polygon. And that's what I'm doing in that weather hazards demo. I actually discard the storms polygon, replacing it with a polyline, then passing it through a buffer. I change the polyline back to a polygon, so I'm constantly changing the event record's geometry type. The intersector processor is another one of the geometry processors that does an overlay operation. It generates a geometry that represents the intersection, or that snip, that portion of the geometry that actually intersects one or more geofences. So if I were to bring in a polygon and compare it to another polygon that was a geofence, only the area that intersects those two geometries would be output from this particular processor. And again, I can either enrich the record by adding that processor result as a new geometry, or I can replace the existing geometry. It's probably important to note here that event records are not the same as feature records. A feature record in a feature class, of course, can only have one geometry, and it has to be consistent, point, polyline, polygon. With the GeoEvent Server, a geometry is a geometry. I can have more than one of them. It's just another attribute on an event record. I can also change the geometry's type on the fly as part of my real-time analytic. Another demonstration now, finding patterns in data. What I'd like to do is demonstrate how we can count the number of crimes that are occurring in an area and dynamically alert when the number of crimes exceed some given threshold. I'm going to call up my different web map for this demonstration. And while that patterns web map is loading, I'm going to come over to my GeoEvent Manager and turn off some of the inputs that I was running for the prior demonstration. So I need to turn on a GeoEvent service that's going to perform my counts, and a GeoEvent service that's going to receive the crimes that I simulate using the simulator. So now that I have my services running, I can begin simulating some crime incidents. For this demonstration, I'm going to be simulating one crime every 100 milliseconds. So if you have family or friends in the DC area, don't be worried. This is just demo time. As I begin playing that data, you'll see some crime dots that start to appear on the screen. And I'm going to go ahead and pause that simulation for a second to show you something else that's going on with this analytic. The one service is processing the dynamic buffer, or the dynamic events as they come in order to render them as geofences. So as I was saying, using a stream service, I'm bringing all of those crimes in, and the geofences are actually the points, not the polygons. And as you hover over any one of these crimes, you'll see that I have calculated a start time as when it was received, and dynamically an end time that was 5 minutes from when that crime was received. So now I'm managing the geofences and automatically allowing GeoEvent Server to discard geofences that have expired so that I can manage my memory. Go ahead and start the simulation again and allow some additional crimes to come in. And over on my GeoEvent Manager, I'm going to poll for that fishnet of grid cells that you see represented, so I can start looking at the count of the crimes in those polygons. So my input here is going to poll about 5,000 polygons. There we go, 5156 polygons have just come in, and that process has processed 240 of them as it discovered some of them intersect crimes. I can come over to my portal web map, and as I zoom in on a portion, I can click one of those grid cells and obtain a count for the number of crimes that are in that area. These counts are being dynamically adjusted as every poll, every 60 seconds, reconsiders that fishnet grid and counts the polygons that are inside of it. Eventually, the number of crimes will start to pile up, and we're going to see an alert as a red flag that more than 10 crimes have occurred in an area. Looks like my timing and my description was a little off there. I'm a little ahead of the demonstration. There we go. So we've popped a flag now as an alert to say that this grid cell has more than 10 crimes that have occurred inside of it. And if I click just on that alert, you can see 10 or more crimes, and there's a started timestamp that now I can start to monitor the duration of that incident. So let's take a look at how the analytic works behind that particular example. The top part is processing the polygon that was pulled out of the feature service, and if there are no crimes that intersect that polygon, a field calculator is writing a 0 as a new count into a field. If that new count is not the same as the old count, then I'm updating the feature record in the database so that the next poll I understand there was a crime, one or more, that occurred in that area. The bottom part of the analytic is a little more complicated. If there are any crimes that intersect that given polygon, then I'm going to use a geotagger to pull the identifiers for those individual crimes and use field calculators to determine the number of crimes in the area. The last part is an incident detector, and that I've configured with that threshold that if 10 or more crimes are detected inside a polygon, I want to output a new event record that's going to display it as a feature flag on that web map. Let's look at the geotagger in particular. It's going to enrich events with a geographic context. When a filter expression evaluates as true, the event record will be enriched with the name of the geometry that it shares a relationship with. For example, here I have a geofence that I've imported that represents a particular gang area in Southern California. As an event record arrives, if the point that is associated with that event shares a relationship with the gang area, then I will enrich the event record with the name of that geofence. In the demos example, I'm enriching using the names or the identifiers for the crimes that occur in a polygon. So I'm going to get out a comma-separated list of all of the crimes that currently spatially intersect the polygon that is being processed. A pair of field calculators, then, are used to determine the actual count. Field calculator calculates a value. You configure an expression, and that expression can be mathematical, it can be string-based, it can also invoke certain Java string functions as wrappers. For example, maybe the event record comes in and its distance is measured in feet, but what I really want to do is report the distance in miles, so I configure an expression distance divided by 5280, and now my output record reports the distance in miles. Again, a field calculator can add its values as new records to the output event, or it can replace values within the event record. What we did in this demonstration was slightly more complicated. We invoked a replace all function that was a wrapper around the Java's replace all function, that one or more occurrences of any character that's not a comma, that's my regular expression pattern, is going to be replaced with an empty string. What that allows me to do then is simply count the length of the string, count the commas, and I know how many crimes occurred in that given polygon. With that, I'd like to hand presentation over to Ken, who's going to look at another example using workforce tracking.
Thanks, RJ. All right, so on your screen, on the screen here, you see we have a map for an area we're watching for some movement of of a workforce, of a field inspection crew. I have a simulator here. I'll kick this off, and we'll start to see a point moving around the map here. This is represents the crew that's out there working the field. So as they move along, they have a device that updates their location with the supervisor, with the central office, whatever you want to consider. When things happen, that device can send that information, but also GeoEvents can simply watch for certain conditions, such as if the crew stops moving for a little while, it'll generate an idle condition. They stop for lunch, for fuel, for whatever it might be. In this case, they use their device to send a message. Hey, just giving an update. We stopped for some fuel and lunch, and you can see that they sent that text to the following phone number. So GeoVences is watching this for the certain conditions, and then when they move on, it closes that event, that idle event, because now they're moving, continuing on their route. And when that crew gets to a certain point, if they stop again, they might send a message. So again, GeoEvents is watching this. In any case, they might send a message to multiple addresses, and so GeoEvents is watching that to see who's receiving those messages. They can log the messages and maintain an archive of the communication that happened with the field crew. Now, what happens if the field crew stops reporting their location? It could be that they're simply changing the batteries in their device, but it could be something more serious. Maybe they were injured or they had an accident or something, and we need to know about that. So I'll simulate that by simply turning off the simulator here and stopping the flow of messages. What we see then is that because GeoEvents is no longer receiving messages from the crew, that's a track gap event, and it's watching for that. So it's different from a track idle that occurred earlier. With a track idle, we continue to receive information, they just haven't moved. In this case, we haven't heard from these guys, and so now we need to maybe take further action. But then GeoEvents is continuing to monitor the feed of information, and if they do replace their batteries or whatever it needs to be, and they continue to resume sending messages, then that incident, that track gap incident, is closed. And we see that here on the map. It would change from red to yellow. I guess I got both of them there, saying that incident is now closed. And so let's take a look at under the hood. I'll go ahead and close my simulator here, and we'll take a look at what's going on with and how that service enables us to look at that the crew's information flow. So taking a look at under the hood at the service, the process for each message begins with the crew's when the crew sensor sends an update or a message indicating their current location and status. The message is simply forwarded to an output that updates the crew's location on a map. All right, this is what allows us to see that moving orange bubble around the map. Now, if the crew sends a text message or an email, in many cases they might send a message with their update, and that message could go out to multiple destinations, multiple recipients. So GeoEvents needs to be able to parse that and keep a log of what messages were sent and to whom. And so we have a processor, a portion of this service that examines those messages for addresses, including multiple addresses, and parses that information for our archive. Now, if the crew stops moving for a pre-designated period of time, if we stop for lunch or fuel or something, we have a part of the process that watches for that. And if an idle event occurs, generates a notification for the supervisor, so that we have a notification that they stopped for a period of time, and we've logged that. And similarly, if we don't receive that information, the update from the crew we get a more serious alert, maybe something's happened, maybe we need to send somebody out there to see what's up with these guys. In cases of either a track gap or a track idle event, one of the things that it will be important information for the supervisor is where that occurred. Now, of course, the sensor is sending its longitude and latitude, but for most of us humans, that's less useful on a case-by-case basis than, say, a street address. So we have a reverse geocoder processor that takes the longitude and latitude, sends it out to a REST service, and gets back the nearest street address that it can find to that point location. And then that information is enriched, or the GeoEvent is enriched with that information so that the supervisor can have a better idea of where that event occurred. So we'll take a look at each one of these processors in turn. We'll start with that field splitter processor. Remember, this is the one that took those multiple addresses that the crew sent a message to and broke them up into individual addresses. And so all this does is take a look at an indicated field and split it based on separating a delimiting character, a comma in this case. We might also have a multi-cardinal field because GeoEvents will support lists of values within a certain field. So think of a JSON array in this case, and can split values from there as well. Basically what happens is when we receive a message that has multiple addresses or multiple values in any field, the field splitter simply takes that one GeoEvent, copies it, and then copies it for each one of those individual addresses. So now whereas one message came in, two messages will actually go out, one for each of those addresses in the field that we split. Now moving on to the track gap detector, and I'll highlight the track gap detector. Conceptually, it's very similar to the track idle detector, so I'll describe the track gap detector in detail and then summarize the track idle detector. But basically, the track gap detector watches for a gap in the flow of messages that's coming from the sensor. And when it detects a gap, it doesn't propagate the same GeoEvent message. It generates a new message, a track gap message that just has a few fields that basically says, that indicates the time, the location, or that it last received an update from that particular sensor, as well as a Boolean value of whether there's a gap or not, true or false. So in practice, the way it works, the first time it receives a message for any track ID that it's never seen before, it opens a log for that track ID. And then as long as it continues to receive additional messages for that same track ID within the specified time window, it's happy. But when the time interval passes without receiving any updates for the track ID, it issues a track gap event with a gap attribute of true, as well as with the geometry and the timestamp of the last received event. And it continues to issue these GeoEvents at each interval of the track gap detector until it receives a new GeoEvent that from that particular tracked asset, that sensor, and at which point it issues a track gap alert or a track gap event with gap set to false. So that sort of closes that state of track gap, and of course it issues the updated geometry for the most recently received location as well as the timestamp for it. So that's the track gap detector. When a gap is detected, the next detector or the next process that we have in the flow of our service here generates an incident. So the track gap detector will generate that track gap GeoEvent. The incident detector watches that track gap message, and if gap equals true, now we're going to generate an incident, and it will start to it will open an incident and then continue to track that incident and the duration and the open status of that incident so that the supervisor can have a summary of when that incident began and how long it lasted if it closes. So the way an incident detector works is that GeoEvents will receive, the processor will receive that message and will watch each message for certain conditions. The conditions could be spatial, or they could be attribute conditions, or both. And then when the condition evaluates to true, it'll generate a new incident, and the incident, the schema, the GeoEvent message has a very different schema of the incoming message, because it has all the attributes necessary to indicate that this incident was opened, when, where, and what the conditions were that caused it to open. We can also generate a closing event, closing condition, and when that closing condition is met, then the incident detector will actually close the event, close the incident, and issue a new message indicating that the incident has been closed. So here you see that the closed condition was met, and the incident indicates the duration of that particular event, and that it's now closed. So that workflow was very similar to the track idle workflow, where we were simply watching for idle events, and then we followed that up with an incident detector as well, so that we could see how long that idle event happened, and when it started and when it closed. Now, in either case, we followed both of those incidents with a reverse geocoder, so that we could know where those events happened. Now, the reverse geocoder is not an out-of-the-box processor. This is an example of a custom processor that was written with the SDK, but it is available online. So if you need this, you should be able to download that. Really, all it does is take the geometry of an event and send it out to a configured geolocator, reverse geocode it with, and then it enriches the incoming GeoEvent with the new address fields that it received from the REST call that it made to that locator service. And so in practice, it's actually pretty straightforward. When the event comes into the processor, it examines the geometry, which it sends out to the geocode service. The geocode service will return the address attributes for that location, and those address attributes are simply appended to the GeoEvent, and that's the new message that goes out from the processor. So it's fairly straightforward in that regard. So I'd like to just wrap up with some of some summary notes here. But basically, ArcGIS, the GeoEvent server is it's a dynamic platform that allows you to process the real-time data, and in most cases take the human out of the loop. So you don't need to have a person sitting there watching a computer screen waiting for something to happen. The system automates that process, and eliminating or dramatically reducing the potential for error and missed information. There are a number of places where you can turn for additional information about GeoEvents. We have a number of step-by-step tutorials that are available online, and you can download those from the gallery with a simple internet search. We'll be able to find those. We have blogs and discussion forums and GeoNet, so I'd encourage you to peruse those as well. A lot of people are asking and answering questions there, and many of those forums are watched not just by Esri staff, but by you. And so a lot of people, if you have a question or a concern or some kind of a challenge that you're trying to meet, somebody else may already have addressed that, and so you might be able to leverage that information. The video recordings for this workshop, as well as all the other workshops here at the Dev Summit, will be available after the close of the conference. So I'd also encourage you to take a look at those. Some additional technical presentations on the real-time and the big data capabilities of ArcGIS are available here. We had a number of them already. Hopefully you had a chance to attend some of those. but if not, there's still a few yet today and tomorrow. So I encourage you to attend if you will. And then we encourage you please take our survey. You can use the events app and find this workshop and provide your feedback. It really does help us to maintain and keep up to date, maintain the quality of our workshops for you. And with that, if we still have a little bit of time, we'd love to entertain whatever questions you have. Yes, sir. Is the question, will GeoEvents handle 3D geometry? Is that right? In geofences.
The answer is for 3D geometry and geofences not in the near future, because the Java Geometry API only supports spatial conditions that are two-dimensional. So while we could import a geometry that had 3 dimensions, we really can't do a spatial compare of, say, a drone in flight to make sure that it is within its flight corridor. What we can do is consider the geofence to be a footprint on the ground and then use a pair of filters so that we can say, does it intersect that footprint? And if that footprint were extruded to a certain altitude, is the altitude or the height of that event record between 2 threshold values?
Yes, sir.
There is like one stream service, and then there are all these related processes that produce this other outputs, like incidents and errors and all those things. Is there a way to discover the related stream services?
You're asking if there's a way to discover related other stream services? You mean if the stream service is something that somebody else might have published, or if you?
Let's say I have one stream service where the positions are coming in, and you talk about all these GeoEvent processors that are creating other data, right, based on one stream service.
Sure.
How does the client discover what are all the related GeoEvent processors?
So I'll take a stab at answering what I think you're asking. Every event that goes through a GeoEvent service is considered atomic, by which I mean it doesn't know anything about a prior event, and it doesn't know anything, of course, about events that are bound to happen. So if you want to do any sort of analytical compare, say in the example of the dynamic geofences, I had a position and I was comparing its buffer to another stream, I had to import that other stream's geometry as a geofence so I had something to compare against. So no, you can't have 2 input streams and do coincidence between them unless one of the streams is somehow persisted as a GeoEvent, or I'm sorry, a geofence, and then you can compare the one stream's location to the geofence.
No other questions? Thank you very much.
Thank you.